In this video, we will practice rewriting logarithmic expressions using the properties of logarithms. This is AP Precalculus topic 2.12. If you appreciate this content, please give it a like. For each of the following, write an equivalent expression using a single logarithm. The sum of two logs can be written as a single log using the multiplication property. So we can write the log base 3 of 4 times z. The difference of two logs can be written as a single log using the quotient rule. This will be the natural log of x over w. Quick side lesson. If you have several log terms that are being added or subtracted, you can write them as a single log in one step. So we can write log. The fact that there is a minus involved means that there will be a quotient. So there are 4 terms. That will mean we will have 4 factors inside this quotient. It's just a matter of knowing which factors will go in the numerator and which factors will go in the denominator. Any factor that comes from a positive term will end up in the numerator. So log a is a positive term, so the a ends up in the numerator. Log b is a negative term, so the b will end up in the denominator. Log c is a negative term, so the c will be in the denominator. And log d is a positive term, so the d ends up in the numerator. Number 3, we can write these 3 terms as a single log. The presence of the minus tells me that there will be a quotient. Since we have 3 log terms, we will have 3 factors inside the quotient. The log 3 term is positive, so the 3 will end up in the numerator. The log 10 of x term is negative, so the x will end up in the denominator. The log base 10 of 5 term is also negative, so the 5 will end up in the denominator, and I'll just put that in the front. So this is the answer. We don't really need to include the base 10 because it is understood. So I think I will go back and just erase that. Look at this purple rule. The power rule tells us that if we have something multiplying in the front of a log expression, we can take that factor and write it as the exponent instead if we want to. On number 4, we need to move this 3 to the exponent of x before we do anything else. So we will have the log base 4 of 6 plus the log base 4 of x to the 3rd power. On number 5, the 5 and the 2 in front need to be moved to the exponent of the x and the exponent of the y before we get started. So we have the natural log of x to the 5th power plus the natural log of y squared minus the natural log of w. Now we can combine all 3 terms into a single log by realizing that the 3 terms will become 3 factors inside this quotient. I know it'll be a quotient because I do see a minus sign right here. So natural log x to the 5th power is a positive term. So the x to the 5th power will end up in the numerator. Natural log y squared, another positive term, so y squared will be in the numerator. The natural log w is a negative term, so the w ends up in the denominator. Number 6, the x in the front needs to move to the exponent of the 2. So the first term becomes log of 2 to the x power minus this 3 will be moved to the exponent as well. So we have log x to the 3rd power minus this 1/2 will be moved to the exponent. So we will have minus log y to the 1/2 power. Remember that the 1/2 power is the same thing as the square root. So when we combine all 3 of those into a single log, The minuses tell me that we will have a quotient. the three terms will become three factors in this quotient. The first term is positive, so 2 to the x power will go to the numerator. The middle term is negative, so x to the third power will end up in the denominator. The third term is negative, so y to the 1/2 power will also end up in the denominator, but because y to the 1/2 power is the same thing as square root, I'm going to write it that way. Number 7. Which of the following expressions is equivalent to log base 5 of 3y to the 4th power over z squared, where y and z are positive constants? I see three factors inside this quotient, so we can rewrite this log as three separate logs. So I will have log base 5 of 3 because of the first factor that I see, and any factor that comes from the numerator will become a positive term, so I'm going to leave this positive. Next I see the y to the 4th power, so I'm going to put plus log base 5 of y to the 4th power. I'm putting plus because y to the 4th power came from the numerator. Next, I see the z to the 2nd power. Because this is in the denominator, this will give us a negative term. So it'll be minus log base 5 of z squared. Any of these exponents inside the log can be brought to the front. So I'm just bringing down my log base 5 of 3. But then this 4 will come to the front, and I will have 4 log base 5 of y. This 2 will come to the front, so minus 2 log base 5 of z. So looking over the answer choices, the answer is C. Number 8. Which of the following expressions is equivalent to natural log 5e squared over the square root of x, where x is a positive constant? So I see three factors inside this quotient. So I can rewrite this using three natural log terms. Natural log of 5. This comes from the numerator, so I will leave it positive. And then I will have natural log e squared, also the numerator, so also positive. The radical x is in the denominator, so I'm going to have negative natural log radical x for this term. Let's go ahead and write this as natural log x to the 1/2 power instead. All right, looking ahead, I don't see any square roots. And radical x is the same as x to the 1/2 power. This 2 can be put to the front, and so can this 1/2. So I will have natural log 5 plus 2 natural log e minus 1/2 natural log x. Okay, natural log e can be simplified, because this is really a side lesson. Natural log e is really log base e of e. E to the 1 power is e. Therefore, natural log e is 1. Go ahead and memorize that so you don't have to think through that every time. So if I replace this with a 1, then we simply have natural log 5 plus 2 minus 1/2 natural log x. So looking over the answer choices, okay, there's my 2 plus natural log 5 minus 1/2 natural log x. The answer is A. Number 9. Which of the following is equivalent to 3 log x minus 2 log y plus 1/2 log 16, where x and y are positive constants? Because of the power rule, these numbers in the front can all be moved to the exponent. So I will get log of x to the third power from the first term minus log y to the second power and plus log 16 to the 1/2 power. However, we know the 1/2 power is really square root. So I could just leave it like this temporarily, or I could go ahead and make it a square root. Either way, the square root of 16 is 4, or 16 to the 1/2 power is 4. So I'm going to make that change as well. I'll make it on the next step. So all three of these can be combined into a single log term. There's going to be a quotient in the middle of it because of the minus sign. The first term is positive, so therefore the x to the third power will end up in the numerator. The middle term is negative, so therefore the y squared will end up in the denominator. The third term is positive, so whatever comes from this will be in the numerator. But the square root of 16 is 4. So I'm going to have a 4 in the numerator. I will go ahead and put that in the front. So I'm going to go ahead and start looking for the answer now. 4x to the third power over y squared. The answer is C. Number 10, which of the following expressions is equivalent to log base 5 of x, where x is a positive constant? Log base 5 of x is such a basic logarithmic expression. The only way I can rewrite this is to use the change of base formula that says you can take a single log and rewrite it as the quotient of 2 logs. So I'm going to have a log in the numerator and a log in the denominator. I need to remember which goes in the numerator. Will it be the x in the top, or does the x go in the bottom? Where does the 5 go? Well, the way I remember it is the base 5 is low. It's a subscript. It's hanging down low. So therefore, it won't surprise you that this 5 is going to end up on the denominator. The x is higher than the 5. It will end up higher than the 5. It will end up in the numerator. The way the change of base formula works, you can use any base when you change the base. So I can rewrite it in this format, but this could be base 6 and base 6. Or it could be, base 9 and base 9. It can be any number you choose. Or you can just leave it plain. Oh, too far. You can just leave it plain, which means base 10. So if I just stop here, I see that the answer is going to be C. Number 11, which of the following expressions is equivalent to log base 3 of 7? Let's use the change of base formula again. So remember, maybe I can squeeze this in right here. I can rewrite this as a quotient of 2 logs. So I'm going to have log over log. Which of these numbers will end up in the numerator? The 3 and the 7, where do they go? The 3 is low, so it's going to stay on the denominator. The 7 is a bit higher than the 3. It will end up in the numerator. That's just how I remember it. So the way the change of base formula works is we can use any base we want right here. Okay, so like I see a 7. So I could do 7 here and 7 here. All right, I see a 10 on one of the problems. I could do that if I wanted to. I could do base 10, base 10. I can do whatever I want. Now, scanning across the answer choices, the only one that has a 7 in the top and a 3 in the denominator is option D. What would the base have to be to make it be natural log? Well, natural log is base E. So if I choose base E for both of these, then that makes it natural log 7 over natural log 3. That's why the answer is D. Number 12, let f of x equal log base 6 of x. Which of the following is equivalent to f at w minus 3 times f at z, where w and z are positive constants? Let's see. I need to do f at w, and here's f right here. So the f at w part is going to become log base 6 at w. All right, this is f. F at w means plug in w. And then you see that we have the minus 3, so I'm going to put minus 3 times. Next we have f at z. That means take function f and plug z in. So this part will be log base 6 of z. So we need to rewrite this to match one of the options. All of these are written as a single log, so let's condense. We have learned that when you have something multiplying in the front of a log, you can use the power rule and put that number as the exponent. So I can bring this down, log base 6 of w minus log base 6 of z to the third power. Make that 3 the exponent. Now we have learned that when you have the difference of two logs, you can condense that down to a single log. Log base 6 of, it will become a quotient. It'll be the first factor divided by the second factor. So log base 6 of w over z to the third power. And then we look up, we look around. Aha! The answer is B. Number 13, let f of x equal log x and let g of x equal log of 4x. Which of the following statements about the graphs of f and g is correct? Notice how similar these are. How does function f compare to function g? Notice that g of x is the same as f of x, except function g has a 4x on the inside instead of just an x. So what transformation is it when you multiply by 4 on the inside like this? Well, anything that you are doing on the inside of the function is a horizontal transformation. So the answer will not be C or D. Multiplication causes a dilation. So this is going to be a horizontal dilation by a factor of 1/4. It's always the opposite of the way it looks with these horizontal transformations. So the answer is B. Number 14, let h of x equal natural log x and let k of x equal natural log 8x. Which of the following statements about the graphs of h and k is correct? Notice that the only difference between h of x and k of x is that k of x has this 8 multiplied on the inside. This means that k of x is a horizontal dilation of h of x by a factor of 1/8. It's always going to be the opposite of the way it appears when you do a horizontal transformation. Think reciprocal, 1/8 instead of 8. The only problem is when I look at the options, this is not one of the options. This is a true statement, but it's not one of the choices. Let's try a different strategy. Let's go through the options one by one. We will set up the transformation described and see if it gives us whatever they say it's supposed to give us. For option A, we need to do a horizontal dilation of the graph of h by a factor of 8 and see if that's equal to k. So a horizontal dilation of h means we're going to take the function h and multiply by something on the inside. Because the dilation is by a factor of 8, we would have to multiply by 1/8. You do the reciprocal. The question is, does this expression equal k? Does this expression equal natural log of 8x? Clearly, it does not. It should be an 8, but we have a 1/8. So A is not the answer. For option B, we need to set up a horizontal dilation of the graph of k by a factor of 8. So here is function k. So we have the natural log of, I'm going to leave a little bit of space here for the transformation, but the natural log of 8x. This is function k. If we want to take this and do a horizontal dilation, we're going to multiply by something in front of this. If we're doing a dilation by a factor of k, we actually need to multiply by 1/8. So what does this simplify down to? 1/8 times 8, those cancel each other out, and you get the natural log of x. But guess what? The natural log of x is h of x. So we have just shown that a horizontal dilation of the graph of k by a factor of 8 is the graph of h. So the answer is B. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.